conclusions from 3-point, 5-point, 10-point, 1-point linear models for making predictions based on temporal data sampled at regular intervals.
10-point was the best.
10-point was the best?
And naive was...
Well, better than 5-point or 3-point, right?
Yeah.
So more model gives more data gives better results.
My naive was my second best one.
And what do you mean? How did you measure best versus second best?
I guess the RMSE value was the closest to 1 for 10-point, and then all except for the U, the naive was the second closest to 1.
Was it better than the 10-point model for 3 of the 4, but for the U it was actually better?
No.
I remember something about the naive model from previous years where actually the 10-point model sort of beat it on the U RMSE or something. But
that's what happened to me.
Yeah.
The naive model was second best in U and best in V and magnitude.
yeah. So what I wanted you to get out of this assignment is that in many cases more data is indeed better. I'm going to have to look at maybe your implementation of naive. But generally, the naive model is you use 2 data points. Well, you really only use 1 data point, but you also have the data point you're trying to predict as your target using that prior data point. And your prediction for that target is just to use the prior data point. Just assume that whatever the world is like today, it will be exactly the same tomorrow. Nothing ever changes. And on a short enough time scale, going from one 20-minute period to the next, 1 hour to the next, maybe even 1 day to the next, the average temperature today is pretty much the same what it was, or the high temperature, I guess, even, or average temperature, both, is pretty much going to be the same as it was yesterday, right? Today's high is pretty much the same as yesterday's high, a couple degrees off maybe, but pretty much the same. And we could also predict today's temperature by using the prior 3 days high temperature to predict today's high temperature. We better predict apples to apples here. Although we could probably use the prior 3 days, throw in the prior 3 days average temperatures as well. Maybe that helps stabilize our predictions. But in general, if we use the same data values and we use prior readings of those values to predict the next value in the series, that generally works fairly well. And I do observe that by adding more data to that series, by essentially joining that table to itself more times, the prediction gradually improves. Did you experience that, Mr. Kapiski? Didn't quite finish?
Not quite.
Yeah, okay. Sam, how about you?
No, I didn't do it.
Didn't start?
Well, I haven't started the last couple, so.
Devin?
I got turned in, but my 1 point versus my 10-point was way off, so I'm pretty sure I messed up there.
Oh, okay.
Yeah.
How about you? Dan?
I think I did it wrong.
Pardon?
I think I did it wrong.
Oh, okay. So we were talking about how for that homework 5 assignment, did you turn that one in, Aiden?
Probably the Excel stuff done. I don't have my graphs done though.
Oh, okay. Did you, but you have results for 3-point versus 5-point. Did you experience that the 10-point model was had a lower RMSE, average error overall, than the 5 points or the 3 points?
Yeah, I didn't do the RSMD yet, but
Okay.
generally I kind of try to compare it and it looked a little weird.
Yeah. I would like to find words to describe that weirdness. Mr. Head, were you able to complete homework 5? Not yet. That's so unfortunate. Although you are in good company. However, know that there is homework 6 due 1 week from today, and so we're rapidly falling behind if we're not turning in our work here. So try to get that turned in. So anyway, this is my after-action report from last iteration's homework 5 in this class. And I'm just focusing in on it. What is this? This is, I guess, a 2-day period? No, just a 24-hour period, July 2nd, the day that the storm occurred. And so this looks a little bit different from like the 3-day version where all the data is more crushed together. But what we have in this particular graph is, on the blue line is the actual U values that we're trying to predict, and then the orange is the predicted U values, which mapped to the same X value should give us, this was the actual value, and then this was the predicted value for that time. And I imagine this is probably pretty similar to what everyone acquired with their 3-point linear model approaches. How would you describe that, those two series of lines, Dalton?
Well,
If you had to describe it to somebody with limited vision in the back of the classroom here, what are those two lines showing? What is that? What is the validity or the goodness of that 3-point prediction orange line compared to the actual data? Would you say?
It feels a bit like the actual goes up, and then like a couple values later, the predicted goes up.
How many values later do you think?
I'd say like maybe like 1 or 2.
Yeah, I think it is pretty much 1. What you're describing is lagging predictions, right? So we are making predictions, but it does appear, I can probably turn on a laser pointer here. What I'm really noticing is this peak here in the actual data, and then the predicted data also has a peak, but it does seem to be 1 item further on. I would like to say 1.5 items further on, but I didn't do predictions on the half points, and so that's either got to be the very next the very next time slot or 2 time slots away, like you said. I suspect it's only 1, but I might be wrong. And then what's happening here, Dalton? Can you explain this peak in the actual data, and then this actually went down? And then we've got these 2 points here. What's going on here, do you suppose?
It could be that it sees that it drops right after that peak. So it predicts it goes up and it actually goes down.
So you're saying the model sees 2 spots into the future and it sees that the blue line is going to drop. The prediction model doesn't see two slots into the future, probably.
So it like.
What is that big drop? Can anyone interpret that one for me?
I think it's the drop beforehand in the actual, and it's thinking that it's gonna drop like that, so it predicts that it's gonna drop and it goes up instead.
Yeah. From my Excel experience, what I think this is, since I like to connect dots with lines, and I don't particularly like to see the markers, maybe markers would be helpful in this situation to see how many actual readings are on that line. I believe I've got some missing data here from that big blue point, and then the drop all along here. I don't think my table actually had data for all of those points here during that data. It's as if almost the storm knocked out the sensor in Bemidji for a little while. I'm not sure, did you guys see that in your data, in your homework 5 data? Did you see some missing data suspiciously close to the storm time? Because this is what happens when we try to join one table to itself repeatedly, is if there's just one missing data value and we join the same table to itself 3 times, say, then that's going to cause 3 subsequent, or 3 consecutive values in the 3 subsequent time values in the subsequent series that didn't get joined together. And so that's going to create a whole of length 3 in our time series. And if also in the original data there were 2 points in a row that were missing, now that whole extends out to a 4 time periods, et cetera, and so maybe the Bemidji wind station came up and down and up and down, and maybe it collected 1 or 2 readings and then went down again, and then came up and collected a reading and went down and another 1 or 2 readings during that time. But if ever there were never 3 consecutive readings, that's what we're counting on here. Actually, it's 4 consecutive readings. We joined that table to itself 4 times so we could know what the target value was that we were predicting from the 3 prior values. And so yeah, if ever there were never 4 consecutive values taken in consecutive 20-minute sections, then this whole could very well be very long. Until we can finally get 4 consecutive values again. And then we get this combined row, and then we can make a prediction, and then we get that prediction there. So I think that's what happened here. And this is going to get even worse when we try to do a 10-point model, and we're joining 11 tables together. Anytime we don't have 11 consecutive values, we're not going to have a row in our table that we're using to make predictions. The table that we're going to copy paste into Excel. So that's how stuff like this happens. But yeah, I do find very interesting that the 3-point model has this lag to it. It seems like every peak I see in the blue line, I see that peak repeated in the orange line as long as there was data in the consecutive next time slot to create a joined row in. And so yeah, I see a little bit of a lag in the 3-point model. Did anybody notice a lag in your 3-point model graphs, those of you who turned it in? Did you see a lag, Stephen?
Yeah.
Matthew, did you see a lag? Did you mention it in your report?
Yes.
That's what the report is for. Mention weird stuff like that. You told me to make this model. I believe I've made this 3-point model to the best of my ability. And Professor Neville, your 3-point model sucks. It just gives me laggy predictions. It predicts important events after they actually happened. What good is that? And so the RMSE that I'm having you calculate, that kind of hides the fact that, yeah, okay, this is a decent RMSE, plus or minus 3 wind units or whatever, but they're consistently late. That's terrible. Well, it's not optimal anyway. It's probably the best we can do with a linear prediction model, and the whole reason we're doing a linear prediction model is because it's sort of easy. We just figure out M and B, and then boom, we have our answer for the next data position. This is the 5-point model. Hey, Dalton, do you detect any lag in this model?
It's looking very similar. Like if you look at the peak and the drop before the big one, it looks like it literally is just like one slot over. If you brought it back, it would almost match.
Yeah. And I'm not even sure that this is again, I probably need markers on this to make more sense, but I feel like this is a 2 time slot lag. It doesn't really look like it. I see a dot here, I see a dot would be here, and I don't know if I'm missing a dot here or if there just wasn't a row. Dot here, there's a bend, and so this thing, I don't see like 2 bends before this thing here. So I'm not sure. Actually, I mean, if it were 2 away, then it would be 1, 2. If
We need a level to see where the
we
points line up.
we really need markers. I dropped the ball on that one. I do tend to just like lines, but if now I'm trying to figure out how laggy is my terrible ass model, then I probably need to have markers on each of those so I can see how many markers are between the peak in the actual data and the peak that occurred in the prediction. So yeah, my 3-point model was laggy. My 5-point model, which Stephen assures me was better than the 3-point model, RMSE wise, right? And the 10-point model was even better. More data is more better, Dalton. That's what I want you to get out of this. Would you mind trading lagginess for, general goodness of RMSE prediction values? Would that be okay? No? Yeah, that doesn't seem wholly satisfactory to you. But 10-point model was even better. Here's my 10-point model. I expanded the range of the data a little bit. So I think this is the whole 2-day period from July 2nd to July 4th. I think this is what I asked for. Again, I see the first blue peak here replicated here. It does seem to be a little bit later. Again, I don't think, where is this blue peak? Is that it right there? Here's the blue valley, and there's that repeated. Valley, repeated. A general peak in that sort of mountain of that sort of cluster of peaks there, and then an orange peak. And again, I don't really know how much the lag is, but I'm going to try to tell you that I think this is a lag of about 4 or 5 time slots. Why do you suppose that my guesses for these lags are about half of the points that I used to make the prediction in the first place? A 4 or 5-point lag for a 10-point model, a 1 or a 2-point lag for a 3-point model, a 2 or a 3-point lag for a 5-point model. What could connect those things? Tyler?
I believe it's because it takes the sum of all the, like, for the 10-point one, it takes the sum
Sure.
of the previous 10 points.
Yep.
And divides it by n.
Which is 10.
Yeah. Oh wait, no, that's 10.
Yep.
It's something to do with it summing. I just forgot why.
It's something to do with the slope. When you figure out m, whether it's based off of 3 points or 5 points or 10 points, you're taking the sums of all these things and dividing them by the count or whatever. But the slope for that line, that line is just something abstract that we're creating to try to connect those 3 points together. But where is that slope the truest? Is that slope really that slope at the beginning of that line, at the end of that line, or in the middle of that cloud of points? The middle of that line. I think the slope that we are getting is the slope for the middle of the prior n points. And so by the time we are making our prediction for time next, for a 10-point model, we're using a slope that's 5 points old. And I think that's why we get this half size lag, half the number of points we use to figure out the slope lag, because that gives us a slope that is about that old to predict our next point by. So it's rather surprising to me. I do love the fact that we're using an increasingly old slope. We're still getting better results according to our RMSE on average. Another thing that I kind of notice that's more obvious on this 10-point model than the smaller distance models is the more points you use, the smoother your slope approximation is going to be. And that also makes this graph smoother. This sort of mountain that's passing through the jagged series of peaks in the blue signal. It's not a jagged series of orange peaks. It's basically one big smooth orange peak that kind of follows more or less what was going on. It's going through the middle of the maximum values and the minimum values in all of those blue peaks and valleys, and it's just sort of charting an even course in between those two places. I think that's a contributor to why the RMSE for the 10-point model is so much better. It just smooths itself out and it passes between the maximum and the minimum values over that particular time period. So yes, it is laggy, but also it isn't quite as responsive as the 3-point model was. I probably have a 1-point model here, the naive model. I do not have the 1-point model here. But what does the 1-point the naive model look like? It's going to look like, well, actually, Dalton just described it a little bit ago. We can tell that this orange prediction line is not really at all a copy of the actual data line, the blue line here. These are honest predictions using slopes, and then they're honestly wrong, but you know, they are sticking pretty close to the true line, even though they are lagged by at least one time slot. If I were to do a naive model on that blue line, it would look like an exact copy of that blue line. I would color it another color, probably orange, or maybe if orange was already there, maybe something like purple. And anyway, that copied series would just be moved over exactly one time value, right? And it would be an exact copy of this graph. It would look exactly like the same thing lagged by one time value. And you're looking at a graph like that and you're thinking to yourself, that is a terrible predictor. It is guaranteeing that all of its predictions is exactly one time unit later than the value actually happened. What is that RMSE going to be? And weirdly, it's smaller than the 5-point predictor and the 10-point predictor. Maybe the 10-point predictor did manage to beat it once. But consistently, all of those multi-point slope intercept predictor models don't even work as well as the naive model. And this is a known fact within scientific endeavors, is that when you're trying to build models to generate predictions like that, always test them against the naive model, because the naive model is super simple. A monkey can operate it. You're just copying the values that are coming to you and saying, the next value is going to be exactly the same value as I got just now. And you know, you're never going to be correct. But in general, we've noticed that yesterday's high temperature was pretty much the same as today's high temperature. When the distance between two readings is not very far, the difference won't be very much either, and so you do naturally end up with relatively slow RMSEs with the naive model. The naive model is super hard to beat. You know that you've got $1 million prediction model if it can beat the naive model. I don't think most prediction models can beat the naive model consistently. So, naive model is a great test for your computer models, which generally never makes you feel good. But at least it doesn't allow you to think that, oh, hey, I've got something that I can take over the world with now. People are going to want to support me in this endeavor. I'm going to be able to predict their stock fluctuations and make them all billionaires. And so that's why I wanted to teach it to you. That's why in homework 6, I'm also going to ask you to compare your results against the naive model, just because it's easy to compute. There's no computation to it. It's just copying, and it gets a pretty good result. And if your model can get a result that's close to that, that in itself is a victory. I'm not going to promise you that anything I ever teach you is going to beat the naive model. I spent my entire graduate career trying to get my PhD degree, trying to beat a naive model. I never did it once. Luckily, that's not required to get a PhD. Otherwise, there would be many fewer PhDs in the STEM world. But it provides a good measuring stick. So that's what I noticed from these, essentially these temporal models, time-based regression models, y equals mx plus b models, is that the more data you provide, the more historical data you provide, the smoother that prediction is going to be. I suspect that at some point, the number of historical data points that you use to generate that slope, you're probably going to level off in how much they're improving. I doubt if we use like 24 hours worth of data to predict the next hour of data, it's going to give you much of a better result than just using the 10 prior hours of data. At some point, there's going to be a decline in the improvement of these models. But at least from 3 to 10, the improvement was pretty obvious. That's why I didn't ask you to build me a 24-point model. Plus, what would have happened if I had asked you for a 24-point model when I lost my connectivity or whatever happened to that sensor a time or two during that storm? I would have had a gap that was huge. So that's the other downside, is if you need consecutive data, any gaps in the original data record are going to be magnified by the number of times you needed to do that self-join to generate a consecutive data record to predict from. So, I guess my conclusion from homework 5 is the naive model is the best model we've seen so far. But maybe putting a bunch of data together is better than trying to predict something based off of 1 or 2 values. And so if we have more data available to us than just the value we're trying to predict, like I said on Friday, if we're trying to predict U, we also have the V values, right? Maybe the V value, the direction and the speed of the wind in the V direction has some bearing on how much energy is going into the U direction of our reading. Why aren't we using V's to predict U's? And hopefully I gave you the tools in Friday's lecture, basically that regression tool in Excel, to allow you, if you have a table full of data that can be used to predict, say, the next data value in a series, to use as many of those columns as you want, even if they're not the same data type that you're trying to predict. Even if it's not all U's that you're using to predict U's. Because here we were always using historical U's to predict next U. But maybe I should investigate historical V's. Maybe I should investigate historical barometers. Maybe I should investigate historical humidities. And that's just the raw data values that we have. We can also process those data values. Some people say it's not the raw values themselves that are important, it's like the differences between them. So don't even use the raw data values. If the barometer pressure dropped from one time period to another time period by, I don't know, this value X, use that difference value in your prediction rather than I mean, how can you represent that? If difference is important, how can you represent that difference with raw values? You have to provide 2 values to represent that difference. And then the model has to figure out, oh, I have to subtract this one from this one. But if you provide the difference, if that's what's affecting the next wind speed, then your model has that all in one number. And so, even though we have 4 different types of raw values here, we can combine those in different ways and get derived data values that might be just as or even more helpful than using just the raw values. Still though, that requires time and testing and effort. And so for homework 6, I'm not asking you to use derived values unless you want to, unless you have some reason to think that they might be useful to you. I'm just saying, just use more raw values. If you're trying to predict the wind speed in Bemidji, sure, you can use historical wind values if you want. Use V as well as U. We know that using some U's work. The more U's we use, it works a little bit more. But maybe putting V's in there will help with that lagging problem. Also, spatial data values. I've been talking a lot about temporal data values here, but here we are in Bemidji, and we've got a wind station here. What other communities around here have wind stations according to that wind table? Did you guys look up that stations table and find your hometown in it? To see if your hometown had a wind station? You guys are very incurious, aren't you? Right next to Bemidji, Minnesota, I found Lincoln, Nebraska. Lincoln, Nebraska has a wind station. Duluth, Minnesota has like 3 or 4 of them. Minneapolis, St. Paul probably has a dozen. But I don't know. Probably whatever wind is blowing in Bemidji is not the same as the wind in Minneapolis. So maybe Minneapolis wind isn't very predictive of Bemidji wind. But what about Park Rapids wind? Park Rapids is pretty close, right? What about Grand Rapids? I mean, even Thief River Falls. A bunch of people just drove to Thief River Falls and back. How far was that? Like 2 hours? I don't. Is a windstorm big enough to cover 2 hours of drive time? Maybe not, but thunderstorms are pretty big on those maps that I see. Sometimes they seem to cover half the state in width or height or something. And I mean, we do have U and V values and barometer and humidity values for Thief River Falls and Park Rapids, I believe. Here's another thing. I don't know if you've ever stood out in your backyard or in a field in northern Minnesota as a storm blew in, let's say in August or November. Does it tend to come from the same direction mostly? Behind my house, I have a little hobby orchard filled with apple trees. I'm out back there a lot. And it seems to me when rain is blowing into Bemidji, it's always coming from the west, the other side of my orchard or my backyard to my house. It mostly seems to come from the west. And so if we're thinking about joining non-Bemidji data to Bemidji data, if we're thinking about other towns to join our Bemidji data to, maybe western towns would be good for that. Although, I mean, I'm no expert on weather. Maybe during different seasons, windstorms come in from different directions. Maybe in the springtime, the wind is coming from the east or the north. I don't know. How could I test for that in my homework description? So I should probably start talking about my homework 6 description that's due 1 week from today, I think. 1 week from tomorrow is our last day of class before Thanksgiving. So I do want to give you a more full description of this homework. Where is it? There's by the end of class today. I haven't left myself a whole lot of time for that. But all day today, I've been trying to build my way up to the basic concept of this homework, where I want to combine temporal data like we had in homework 5 with data from other locations, spatial data. And we can temporalize those things too. Maybe if Thief River Falls is like a 3-hour drive from Bemidji, then maybe using the wind that was blowing in Thief River Falls 3 hours ago will be pretty good for predicting what the wind will be doing in Bemidji 1 hour from now, 1 time unit from now. So I'm combining spatial and temporal data. As a note, you can work in teams and turn in one report for 2 people if you like for this assignment. I know that computer programmers do like to do their own work. So, of course, you are free to collaborate with other people in this class, work with other people, and turn in your own report. That's what I see the most often, but if you want to turn in a report as a team, that's fine too. Okay, so since I want to know a little bit about what I'm doing before I'm doing it, I just suggest that you run the same tests that I did when I came up with this assignment and started testing things. If I want to look at a collection of towns to the west of Bemidji, I've given you a sample of a few. You don't have to use mine. But I chose Park Rapids, Thief River Falls, Detroit Lakes, and Foston. They all seemed like they were somewhat west of Bemidji, some were north of Bemidji, some were south of Bemidji. I mean, it would be perfect if I could get a southwest, northwest, and straight west town to Bemidji, but that's not how towns are located in the landscape, and so we just take the wind stations that are available to us. And my ultimate goal is I want to choose 2 of these towns. And so I'm just going to investigate a smattering of towns that I recognize that are to the west and pretty close to Bemidji, and then go through that stations table. I mean, just display all of the records of stations in Minnesota, and you should recognize a bunch of towns that are to the east of Bemidji, and choose 2 western towns, 2 eastern towns to combine with Bemidji's data. And how are you going to choose 2 towns out of the 4 or 5 names that you recognize and that when you look at it on a map you realize, oh yeah, they are pretty close to Bemidji? It turns out that there's a lot of stations in that station table that are no longer active. They haven't been collecting data for a while, and so when you look up those W bands in the actual wind table, there's nothing associated with those guys, and so that might knock some values out right away. I think Ely is one of the towns to the east of Bemidji that I was really excited about because I went there during a summer vacation once, and it is this tiny little tourist town, and apparently it has a wind station and no data, so no Ely for me. How can you show me the research that you've done on these towns? I'm going to ask you to, make some graphs. What better proof, Sam, that you've done some good scientific data visualization work, but show me some graphs for wind stations that actually had data. So, and also I probably want to compare them to the data that I had from Bemidji here. It's not obvious to me that Bemidji lost connectivity during the storm here, but maybe if I widened this, I could see that. Really, what I'm looking for here is, does Bemidji have about the same number of dots as the other towns that I want to combine in with it? Out of these 3 towns, Detroit Lakes, Thief River Falls, and Park Rapids, I think I would have to kick Park Rapids out of bed, because Park Rapids seems to only collect data once every hour. So it collects 1/3 of the data that Bemidji does. What does that mean when I try to combine Park Rapids data with Bemidji data with anybody else? Maybe it's only going to connect to 1/3 of the available data rows, right? So you're going to lose a lot of data by including a town that doesn't collect data as often as the town you're trying to predict for. So yeah, throw out Park Rapids. Out of these 3, it looks like Detroit Lakes and Thief River Falls, even though they're kind of far away. But you never know, maybe one of their historical data values will work out for you. One of their lagged values or something. Detroit Lakes, that's okay, that's the southwest and not super far, not as far as Thief River Falls, I don't think, although I don't think I had very much choice left to me after Park Rapids was gone. I had to go out to Detroit Lakes and Thief River Falls from that point on. And I think I kind of have the same problem to the east. I think one of my eastern ones was Duluth, and that's like a 3-hour drive away. That seems, I don't know. Still, I guess I have seen weather maps where storms do range from the middle of northern Minnesota, where Bemidji is, all the way to the edge past where Duluth is. So it's not the worst thing in the world. So I'm going to ask you to choose 2 western towns, 2 eastern towns that has about the same amount of data that Bemidji does, so that when you join their data in with Bemidji data, you don't lose too many rows, like we saw happening with that ever-growing gap around storm time in my 3, 5, and 10-point models here. And so to the east, I found Big Fork, Longville, Pine River, Staples, Waskish, Ely, Duluth. Some are closer to Bemidji than others, but probably your favorite ones will be the ones without data. Because I felt like I had to go to Duluth. I think one year some students actually chose Minneapolis as one of their eastern wind stations just because it had enough data. I mean, places like Big Fork and Green River or Pine River might have data, but they might be like Park Rapids in that their data isn't as plentiful as, isn't queried as regularly, sampled as regularly as Bemidji data is. And so that would also discount them as partners, because it would affect every other table that you tried to connect to Bemidji. Even if all of your other tables collected data at the same rate as Bemidji, just one table collecting data only once an hour is going to restrict everybody's combined rows. Because we're going to use the combined result of all of these tables in one table. And so we want to keep the data loss, or we want to maximize the row count for our predictions. We don't want to only generate a prediction every hour, say, just because Park Rapids is only limiting us to completed rows once an hour. So I guess what I'm talking about is joining 5 tables together, 2 eastern town tables, 2 western town tables, and Bemidji. That's 5 tables just for non-lagged dates. Date A is equal to date B equals date C equals date D. That's going to be 5 tables right there. And you know, I probably want lagged data, but to get lagged data, if I first just join together a vanilla table of those 5 communities, then that table I can join to itself 3 or 5 times in order to get the lags that I want. And I probably don't necessarily need to do a 1 hour ago, 2 hours ago, 1 unit ago, 2 hours, or 2 units ago, 3 units ago, 5 units ago, whatever. I can, if I think for some reason that only, I don't know, 6 time units ago and 12 time units ago are good, then I can skip everything in between. Why would I think that if I'm trying to predict wind, Aiden, that I should think in terms of 3 hours or 6 hours or 12 hours or 24 hours?
Did you say the wind speeds were averaged over time?
Wind speeds are averaged over the 20-minute period. They only give you one value for each 20-minute period, but they probably sampled it several times and then just averaged it together. But yeah, we have no idea how many values they actually average together. And that's not really where I'm getting my 6, 12, or 24 hour sort of thing. But remember how when storms blow through Bemidji, they seem to blow through every couple days? Remember how wind and storms, which tend to generate wind, seem to work on a sort of period, a sort of sinusoidal curve? You remember how I said that I believe it's the turning of the earth that is generating wind? We've got air as a cushion above the surface of the ground where the trees are growing, and as the earth is spinning underneath this cushion of air, it sort of starts turning that cushion of air. Maybe the trees are kind of grabbing at it as they spin past. If it takes the Earth 24 hours to turn, if the Earth is part of what is driving the wind, it makes some sense to me that winds have something close to a 24-hour period. We could ask a chatbot, why not? All of the wisdom of the world is contained within chatbot responses. It's just, that wisdom is sandwiched in between all of the nonsense available on the internet as well. We gotta be able to filter that out. But I bet a chatbot, if we asked it, what is the period of the wind on the Earth or something, maybe a tiny little bit more specific type question than that, it would probably tell us 23.57. The period of the wind is generally about 23.57 hours, which is pretty close to the period of the spinning of the Earth. And so now suddenly it makes sense that storms do tend to blow through town every 2 days on average. Maybe this is when a big storm happens in Bemidji, and so it might take 24 hours. I guess this is 24 hours later. Is it possible for storms to blow through town on subsequent days? Maybe. But yeah, there seems to be something magical about 24 hours. And that means there's going to be something magical about every 12 hours, and that might even mean that there's something magical about every 6 hours. And so when I'm thinking of a natural phenomenon like the wind, I do tend to think in 3, 6, 9, 12 time period increments as potential locations along the timeline to get useful data for my predictions. So maybe instead of joining tables together where the dates are lagged by 1 time period, try 3 time periods, and 6 time periods, and 9 time periods, and 12 time periods, and see which are the best of those. So, okay, now you know that you want to join all of your cities together into one table, and then join that table to itself on, 3 or 6 time unit intervals. This approach could take some refinement, it could use some experimentation. I don't want to tell you exactly what to do, but in order to have everybody sort of give me the same sort of result so I can give you grades based on apples to apples comparisons, I'm providing you with a schema for the result that I want you to build here, and it may not be perfect, it may not be good at all. You might be able to come up with a better one, and if so, I would love to hear about it through your experimentation. But everybody try this one for me, and what I'm doing is I'm taking values from 3 time units ago, and then current values, where 0 is current, and so I'm always trying to predict Bemidji's U and V, basically using V's from 3 time units ago, from Eastern Town 1 and Eastern Town 2, 3 time units ago, and 0 time units ago. So that's what the numbers mean, and the letters after those numbers is I'm just using a current time, what the wind is doing in Western Town 1 right now, and 3 time units ago for basically all of these towns. Again, I feel like, just like the naive model, the closer the data is to the time that I'm trying to predict, maybe the better. So that's why I don't go back more than 3 time units. And I'm hoping that the more data I put together, as long as it's somewhat relevant, then that will generate some improvements too. And all I want is the date for which I'm predicting in Bemidji, and the U's and V's that I'm aiming for. And so really what I'm going to be providing to my model is all of these numbers in black. And these are all raw data values. You could build alternate schemas that are using differences between 3 time units ago, if you think that might help. But just so everybody shows their results on the same problem, I want everyone to do at least this one, and anything else is optional. But if you have some great big idea that you want to test, I'd love to hear about it if it improves upon this. Yeah, I'm doing my joining on ImpNose because different stations do sample their data at different times, and so the date time values never match up, but that's why I created the ImpNo column so that there was always, the same 20-minute period would always match up between data stations. It's we can't really graph this data because this is a 16-dimensional point. Also, one other thing I'm asking you to do is, when you use the regression model in Excel and figure out the coefficients that should be applied to all of the values in these columns, you'll get one coefficient per column here. Only do it for data from July 1st through July 3rd. So that was mostly normal winds plus that one big storm. And we know that between July 3rd and July 5th, on July 4th, another big storm blew through amongst a whole bunch of normal data. And so we're trying to use similar data to generate coefficients and then see how those coefficients work on another 2-day period of similar data, is the idea behind these these training and testing sets. So we're going to generate our coefficients on a training data set, and then we're going to generate figure out the effectiveness of our model, figure out its RMSE on a testing set from July 3rd to 5th. So that's what all of this training and testing set stuff mean. Anybody else read this assignment and have questions about the words that I used? What I'm trying to get at with my overly wordy descriptions? I'll eventually just want you to build a table telling me of various values. Generally, when you train your data on, so I'm going to ask you also to use your coefficients on your training set, and there I'm just demonstrating to you that the set on which you created your coefficients is perfect for those coefficients, and so the RMSE for the training set will always be better than the RMSE for the testing set. That's just normal. But we don't want to actually use our coefficients on the data that we trained the coefficients from. That's sort of like cheating. And so the whole reason we're generating coefficients on a training set is so we can use them for the actual predictions on the testing set 2 days later. This might be for a case where, say, we know that the Bemidji wind station breaks down during storms. We want to make more than just one prediction into the future before we run out of data. And so we're going to come up with a whole bunch of coefficients for this 1 week period, and we're going to use those coefficients for the next week period. And by the way, during the next week period, we're collecting data so that at the end of that week, we're going to get a whole new set of coefficients for columns that we think pretty much generally work. And we're just going to replace our coefficients for our prediction model every week so that we can, if we lose power for a week, or if our sensors break for a week, we can still use pretty recent coefficients to make predictions for another week until we get new coefficients based on new data. All right, so I think that's all of the time I have. If you have no further questions, I'm going to let you go. Yeah. This is due 1 week from today, and I'll probably be fielding questions on it come Wednesday and maybe even Friday, I assume. So come back with questions next time. Thank you for your attention.